We have a strange problem at the heart of quantum physics. The theory works with astonishing precision, but if you ask, what kind of reality is the theory describing? In other words, what is the ontology behind the theory? The dominant answer is, don't ask, it doesn't matter, just shut up and calculate. How did this attitude become so prevalent? Are physicists too focused on the trees and are losing sight of the forest, as Einstein once said? To answer that, we have to visit the early history of quantum mechanics to uncover how the interplay between science, philosophy, and interpersonal conflicts shaped modern physics.
In 1926, Werner Heisenberg was only 24 years old when he was invited to give a talk at the University of Berlin, arguably the center of physics in the world at the time. Heisenberg recalls, "Since this was my first chance to meet so many famous men, I took great care to give a clear account of the concepts and mathematical foundations of what was then a most unconventional theory. I apparently managed to arouse Einstein's interest, for he invited me to walk home with him so that we might discuss the new ideas at greater length."
Heisenberg's most unconventional theory was an enormous breakthrough. It promised to solve the outstanding scientific challenge of his day, the nature of the quantum world. For nearly 30 years, physicists were aware that there was something wrong with the contemporary understanding of the atom. When you hear the word atom, the image that pops into your head of electrons orbiting a nucleus is almost entirely due to Niels Bohr. Niels Bohr had proposed this model of the atom in 1913. His model was brilliant and provided original insight into the workings of nature, so much so that he won the Nobel Prize for his idea in 1922. However, this model was incomplete. It could only explain so much until Heisenberg came along.
In June of 1925, Heisenberg takes a 2-week vacation on Heligoland, a small isolated island in the North Sea. He went there to rest from a severe case of hay fever. After several days, he recovers and continues his research. Working alone at 3 in the morning, his hands shaken, Heisenberg made a breakthrough. He says, "I had the feeling that, through the surface of atomic phenomena, I was looking at a strangely beautiful interior, and felt almost giddy at the thought that I now had to probe this wealth of mathematical structures nature had so generously spread out before me."
Heisenberg had developed a strange new mathematics on the fly, matrix mechanics. Max Born, Heisenberg's supervisor, and Born's student Pascal Jordan helped Heisenberg expound the structure and implications of his new theory. Long story short, matrix mechanics was the first way in which quantum physics was expressed in a mathematical form that is logically consistent. Soon after, Heisenberg was invited to Berlin to present his ideas. After his talk, Einstein invites him for a walk. Once they're inside, Einstein asks him what he really wanted to know.
Einstein says to Heisenberg, "You assume the existence of electrons inside the atom, and you are probably quite right to do so, but you refuse to consider their orbits. I should very much like to hear more about your reasons for making such strange assumptions." Heisenberg replies by saying, "We cannot observe electron orbits inside the atom. Since a good theory must be based on directly observable magnitudes, I thought it more fitting to restrict myself to these." They go back and forth, and Einstein eventually says, "It is quite wrong to try founding a theory on observable magnitudes alone. In reality, the very opposite happens. It is the theory which decides what we can observe." Heisenberg was completely taken aback by Einstein's attitude, as he recalled later. Einstein told him that his theory will one day get him into hot water. With the two seemingly at an impasse, Heisenberg decided to change the subject.
Heisenberg then asked Einstein for advice on a major career decision. Bohr had invited him back to Copenhagen as his assistant, but Heisenberg had also been offered a tenured professorship in Leipzig, an unheard of opportunity for someone so young. Einstein advised him to choose Bohr. 3 days later, Heisenberg was on his way back to Copenhagen to sit at the feet of the quantum master himself. Niels Bohr was not only important because of his ideas, he became powerful because Copenhagen revolved around his personality, his institute, his reputation, and the intense loyalty of the young physicists around him. This helps explain how Copenhagen became center of authority in quantum physics.
Denmark created and funded an institute specifically for him. He lived in the prestigious Carlsberg House of Honor. He entertained physicists, artists, politicians, and even royalty. Copenhagen became like a pilgrimage site for young physicists, many who were mentored directly by Bohr. Some students literally sat at Bohr's feet after dinner to make sure they didn't miss a single word. Bohr had enormous charisma and authority. Richard Feynman later said even major physicists treated Bohr like the great god. He was brilliant, but often extremely difficult to understand. His writing was tortuous and obscure. His obscurity became part of his mystique. Students often could not understand him, yet admired him deeply.
Heisenberg's dilemma was understandable. He had to choose between the prestige of a professorship and the opportunity to work closely with Niels Bohr. To Heisenberg, his matrix mechanics success seemed short-lived. Not long after, Schrödinger developed wave mechanics. Wave and matrix mechanics were different mathematical tools describing the same quantum theory, but wave mechanics was easier to handle and visualize. Many physicists preferred Schrödinger's approach because it felt more intuitive. Heisenberg was worried that Schrödinger's ideas would eclipse his own. He wrote to Bohr about the situation, and as a result, Bohr invited Schrödinger to Copenhagen for a deeper discussion. Schrödinger arrived by train on October 1st, 1926.
The following quote from Heisenberg vividly illustrates what follows. Bohr's discussions with Schrödinger began at the railway station and were continued daily from early morning until late at night. Schrödinger stayed in Bohr's house so that nothing would interrupt the conversations, and although Bohr was normally most considerate and friendly in his dealings with people, he now struck me as an almost remorseless fanatic, one who was not prepared to make the least concession or grant that he could ever be mistaken. It is hardly possible to convey just how passionate the discussions were, just how deeply rooted the convictions of each, a fact that marked their every utterance.
Schrödinger was exhausted by Bohr's relentless questioning. He ended up leaving Copenhagen unconvinced. No agreement was reached regarding a coherent interpretation of quantum mechanics. The central unresolved issue was the meaning of Schrödinger's wave function.
Later that summer, Max Born discovers that the wave function gives the probability of measuring a particle in a given location. This insight ultimately won him the Nobel Prize. But Born's rule also left physicists with new puzzles. What is measurement? And why does the wave function behave differently when measured? Schrödinger's mathematics, along with the Born rule, had unlocked the quantum world, but at a price, and that price was the measurement problem.
But Heisenberg wasn't really concerned with solving the measurement problem. Heisenberg was worried that Schrödinger's wave mechanics had eclipsed his own matrix mechanics. He was also pondering whether he had made a mistake by returning to Copenhagen instead of taking the secure Leipzig professorship. He wanted another major insight that would strengthen his reputation and improve his career prospects. To achieve this, he turned his attention to measurement, but not the measurement problem. He focused on something less difficult and more likely to yield results: the limitations on what we can learn about quantum objects.
This led him to discover a limitation that is built directly into the mathematics of quantum mechanics. The more precisely you know position, the less precisely you can know momentum, and vice versa. Bohr encouraged Heisenberg to use the term uncertainty principle to describe this seemingly unavoidable trade-off. Heisenberg's uncertainty paper succeeds professionally. Leipzig offers him another 10-year professorship, which he accepts. In June 1927, at age 25, he became the youngest tenured professor in Germany. Bohr sees Heisenberg's uncertainty principle as fitting with his own developing ideas. He calls this broader idea complementarity. Bohr works through many drafts, struggling to express the idea clearly. He eventually presented complementarity at the International Physics Conference at Lake Como in Italy in September 1927.
According to Bohr, you cannot ask what is really happening inside an atom. When no one's looking, the quantum world can only be discussed in connection with the measurement setup. Depending on the setup, quantum objects appear as waves or as particles. These descriptions contradict each other, but Bohr argues they are complementary. Wave and particle descriptions are both needed, but cannot be used simultaneously. Bohr pointed to the Heisenberg uncertainty principle as further justification for the inevitability of complementarity.
According to Adam Becker, Bohr was wrong. There was nothing inevitable or necessary about complementarity. Other interpretations of quantum physics are possible. Indeed, the claim of inevitability is an awfully strong and strange claim to make about any interpretive issue in science, precisely because it is always possible to reinterpret any theory. Yet Bohr was convinced that complementarity was the deepest insight into nature found within the quantum theory.
Both Schrödinger and Einstein were absent from that conference, but the next month, Bohr and many of the physicists at Lake Como assembled again for a prestigious invitation-only conference in Brussels, and this time, Einstein, Schrödinger, and many others were present. The stage for the Bohr-Einstein debate was set.